My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to our International Physics webinar. And today it's our 52nd International Physics webinar. So good evening to all here in Bangladesh, and a very good morning to all those who are watching this program from USA. So hope you are well and safe from Corona pandemic. So all we are know that we are staying in a Corona pandemic situation. So it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. So we have already started our online program. So I think you have already come to know that our Department of Physics, have already started its online program, including online classes and online physics webinar. So we are trying to adjust with this new normal situation. And today, it's a great day for our department. And as we are witnessing a very great webinar with such a big scientist from America. And today, I'd like to welcome you all through a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Astronomy, Ohio State University, USA, in astrophysics webinar. And we have with us here today Dr. Sultana Nahar, Madam, Professor and APS Fellow, Department of Astronomy, the Ohio State University, USA. And she has already connected with us, so I'd like to welcome our Madam. So good morning and here good evening, Madam. So
Assalamu alaikum and good morning and good evening.
Walaikum salam. Assalamu alaikum, Madam. So we are very happy that you have accepted our invitation, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So I think for the viewers have already come to know that we have already successfully completed our 51st physics webinar, and today it's our 52nd. So in those physics webinar, physicists from different countries are coming as a main speaker, and they're delivering their knowledge with our student, and they're sharing their experience with our student. And I think by this way, our students have benefited. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First, I'd like to introduce our speaker, though maybe many of you know about our speaker very well, but I'd like to introduce, and then our speaker will deliver her speech, and at the end we have a time. In that time, anybody can join with us. So I think you have already come to know the title of our today's International Physics webinar. Title is Physics of Phosphorus for a Clue of Extraterrestrial Life, and our today's speaker is Dr. Sultana Nahar, Madam. She is currently working as a professor and APS fellow at the Department of Astronomy, the Ohio State University. Dr. Sultana Nahar, Madam, is a senior research scientist at the Ohio State University. She is an atomic astrophysicist. She was born in Bangladesh, Dhaka, Bangladesh, and we feel proud of her. So as she is Bangladeshi. Her father is Abdul Razak. He was a popular lawyer of Bangladesh, High Court and also Supreme Court. Her mother is Samsun Nahar. She was known for her charity work. She has two brothers and three sisters. She got many awards when she was in primary school and when she was in high school. She took her bachelor degree in science in 1977 from University of Dhaka, Bangladesh. And also she was the first woman graduate of BSS honor in physics to stand first in the class. She received her master's degree in the theoretical physics in University of Dhaka, standing first in 1979. She received her PhD degree in atomic theory in 1979. Dr. Nahar, Madam, is also called the Iron Lady by astronomers. Physicists and astronomers around the world use her computationally intensive mathematical model of the iron atom when interpreting complicated spectra produced by high-energy astrophysical processes, such as those that occur near black holes at the centers of active galaxies. She is also known for her pioneering calculation of remarkable complexity on astrophysical significance process. If we see her educational background, you can see that she has completed her PhD degree in atomic theory in 1987 from One State University, Michigan, USA, and her MA degree in quantum optics in 1982 from One State University, Michigan, USA, and her MSc degree in theoretical physics in 1979 from University of Dhaka, Bangladesh. And her thesis title was Compound Scattering in Nucleons at Low Energies. And she has completed her bachelor degree in 1977, University of Dhaka. So we can see her professional experience, and we can see the job history, long-term position. She was worked as an associate director and chief liaison officer at the Obama Singh 21st Century Knowledge Initiative Award project from 2013 to 2017, and as a research scientist from 2003 to 2015 in astronomy, Ohio State University, Ohio, and as a senior research associate from 1997 to 2003 in astronomy at Ohio State University, and as a research associate from 1993 to 1997 in astronomy at the same place, Ohio State University. She also worked as a postdoctoral fellow in mathematical and physical science in astronomy at Ohio State University, and also other places as a postdoctoral fellow. So you can see his previous position as short time visiting scientist at the Weizmann Institute of Science, Israel, from June 17 to 22, 2018, and as a visiting professor at the Department of Physics, University of Dhaka, Bangladesh, October to November 2017, and as a visiting professor in University of Kashmir, Srinagar, March 2023, 27, 2016, and as a visiting faculty in teaching Department of Physics, Delhi University, Delhi, India, from February to March 2014. And we can see her visiting professorship short term. We can see University of Kashmir, India, and the other places also, Saudi Arabia, and Bangalore, India, and Aligarh University, and other places, Harvard University. So, and membership, she has a elected position about 14 different institution, and you can see her award. So honorary plaque by Department of Physics for the astrophysics seminar and various contribution, and you can see her other awards also. So she has a lot of collaboration with different universities all over the world, and she has a lot of work in his research and teaching and other work we can see. And she works as a referee about 35 journal. So we can see that she was a founder of NORAD Atomic Data. We can see that she has also written a book named Atomic Astrophysics and Spectroscopy, Cambridge University Press, 2011, and she got about 15 research grant. So thanks for all of your patience. And actually, I feel proud to host her in my physics webinar. So thanks, madam, for accepting our invitation. It's my pleasure, actually, and actually, I feel proud. So thanks again.
Okay. Assalamu alaikum to everyone, and also good evening and good adab. And I'm so pleased that Pretam invited us, and I'm very pleased to meet all of you through this webinar. Okay, so he mentioned the topic of the title that I'll be talking today is regarding phosphorus. So Pretam, I'm going to my talk, and if there's okay.
Yeah, madam.
So is it okay, Pretam?
See, everything okay.
Okay, all right. So when Pretam mentioned that, madam, you can say something to inspire our students, okay? So that's why I thought I should write the word physics. You know, physics is the basic of many sciences. Okay, and today we particularly talk about phosphorus. We know phosphorus abundant on our Earth, and why it is a clue for the search for extraterrestrial life. Okay. All right. So this excitement just rose up in the sky just last month, couple of weeks ago, when the Venus, which is called the twin of our Earth, has showed some kind of sign of life. So that is phosphine. Phosphine is made from, phosphine is pH3. So they found in the atmosphere of Venus phosphine, which is now produced by life form. But Venus has a very hot surface. It's 900 degrees, and it has sulfuric acid, thick carbon dioxide, and the pressure down is about 90 times more than the Earth. And the environment is very hostile to any living form, but its atmosphere is cooler and it is in motion, and they found now this phosphine. And you can see on the right, this is the Venus, and this is the now a spectrum of phosphine. So after finding it, it became big news because it could be a sign of life outside Earth. So far, we have not detected any life outside Earth. So this is the one indication there could be some kind of microbe, living in the atmosphere of Venus. All right, so that is very good, but there's an issue. Okay, if it is there, how do we always have to explain in terms of theory, and that theory comes from the basic, like underlying science, the physics largely for this case. So I'll be talking about the underlying science to understand this kind of feature. Okay, and it is very important to understand this science, because if you don't see, there's a large discrepancy between observation and also prediction, and that can lead to many wrong predictions of other stars or planets or whatever spectrum we see. But something what they found, that the predicted the spectrum abundant of phosphine in Venus atmosphere is much less than the observation. That means the prediction had a lot of missing physics. So there's a huge discrepancy between the prediction and the observation, and it is 4 orders of magnitude. All right, so we'll talking later. I'll be talking largely about how you can help understand this kind of observation and reduce the discrepancy or the gap of discrepancy between observation and prediction. All right, so I'll just go over this page once. So there is also speculation, how come we see one kind of living form in Venus? So this is our atmosphere, Earth, and you can see atmosphere, but microbes can be seen within 50 to 70 kilometers from the Earth. So, but we know that meteors or asteroids, they pass, usually they don't come very close to Earth, the big ones, but we do get a lot of heat. But luckily, so far we have been okay until 65 million years ago. That was a huge one when all the dinosaurs died. But this speculation from Harvard University, 2 people wrote. One is Amir Siraj, another, could be advisor, Abraham Loeb. They work on grazing. They say, maybe an asteroid came and passed through the Earth atmosphere. So it carried some microbes and went to the Venus atmosphere in its trajectory. So that's why, probably the virus went there, or microbes, and survived. Do you know there are also super bacteria or microbes? We just found, there was a recent news that some kind of bacteria survive for 2 years outside the space station, like super bacteria. So they can survive in a very harsh condition. All right. So now we can see, this is, everyone knows this one. This is our galaxy, Milky Way, right? And it has about 200 to 400 billion stars, and we are just one of them, maybe near the edge somewhere. So if we are living, all this form, all these intellectual beings, we are all intellectual beings. We live in one of these stars, which is our sun, and it is unusual to think that there will not be any living form in any other stars, right? So we can speculate. We cannot be just unique. There could be other life forms. For example, we did not see any planets before 30 years ago. We speculated there could be other planets, but now we have found about 4,000 planets. All right. So we have been searching for life, alien life, for a long time. So there's another reason that in the space we see all the elements like carbon, nitrogen, oxygen, phosphorus, or sulfur, and iron, calcium. All the elements we see in space, they are all in our body. So there's a speculation that we made from stardust. So this is a standard become now we made of stardust. Everyone knows about it. Okay, all these elements are in our body. So if those elements form ourselves some extraterrestrial process, then it can form in other stars too. So that's why we've been searching for life, other life forms. So in 1985, the program started. Is called Seti, Search for Extraterrestrial Intelligence. So you can see all these big telescopes. They are collecting, the signals coming from space, and whether this signal is actual signal, a meaningful signal, or noise. So that's the thing they are determining. So they are focusing on the red dwarf stars. Red dwarf stars means, the stars which are a little bit cooler, right size, which can have planets. That means there could be life forms in those planets. So it has been searching, and it was searched 20,000 red dwarfs. Okay, so they have got some kind of signals, but to say that it belonged to some life form signal, we more analysis is needed. But it hopes to predict something in 2000 by 2040. Okay, so we knew searching, but this searching for extraterrestrial life, but this has a jump for this search since the detection of a planet in other star. So this is our sun. This is our planets. We used to have 9 planets, but now it is 8. Pluto, we call it dwarf planet. So, and this is Earth. So all these planets, we call them planets if they belong to the star. But if the planet belongs to a different star, we call it exoplanet. So we, starting about 1990, we started to have some speculation that planets exist outside our sun. And in 2004, this is the first direct image that taken in Chile, where we found one planet was going around its sun. So this is an exoplanet. So with this finding, the search for extraterrestrial life has soared. There must be some life form, some living form outside there. All right. So there's another reason to study this exoplanet. So this is the sun, and we are the planet going around it. We are very happy because the sun is the source of energy for us, and it also causes seasons for us. So we see beautiful change of season. We are happy right now, and sun is about 4.6 billion years old. But what will happen to the sun after 5.6 billion years? Okay. Actually, or you can say 6-7 billion years. Our sun, if it is at this size, after that it will become that big size. This is called red giant star. So what happens, when all the hydrogen in the sun will become helium, that means the fuel will finish, everything will collapse, and because there will be a lot of negative charge, there will explode expansion, and that expansion will cause this this red giant, but it will engulf our Earth. So what it means that we will all die, but we have our brain in our head, right? We cannot die. We are not dinosaurs. So we have to find a way to go outside. The human race must survive. So we have been looking for exoplanets which are habitable, like which has water in it. It is solid surface, not gaseous, and it has oxygen. And it is not too close to the star. So heavy radiation will not burn the people to causing cancer, etc. So we have been and searching for any clue of life, and that's why phosphorus became more important, and Venus news was and very, very hot news. Okay, so in the space we have a bunch of telescopes already is just looking for these planets and recording them. But in next year there will be huge very big telescope is called James Webb Space Telescope, JWST, will be launched to space. It will be very big. Hubble has mirror, but it is much bigger than Hubble, and it will study exoplanets and their atmosphere. But if we want to know the what kind of atmosphere they have, that means we have to know the physics of the atmosphere, and so that we can say what kind of condition it has, and so that it is good for us to travel in future, inshallah. Okay, so for example, this is the spectrum of our atmosphere, Earth. Okay, so we know that our atmosphere has largely oxygen, water, carbon dioxide, nitrous oxide, methane, and all this. So if someone from outside was looking at our atmosphere, that life being will see something like this. So these are like sign of living form, or we call them biosignature elements, or these are molecules, but these are various elements. So in those element biosignature, we have carbon, of course. We are made 70% of our body is made of water, right? So we have iron, bone, in calcium, and we have phosphorus. But we don't think about phosphorus that much because we have not studied phosphorus that much. But it is an element in the DNA. This is the DNA, and you see the red dot, they are all phosphorus. So phosphorus plays a very important role, in signal passing in our body. So the DNA is there, pass signal all the time, right? So it plays an crucial role in that. So phosphorus, and this is the cartoon I picked up after Pretam put it in in the flyer. Or so this is a nice cycle, largely for plants. They showed how phosphorus is deposited here. It is picked up by plants, and the cycle is a nice one. Okay, thank you, Pretam, for it. Okay, so this is a cartoon of us. It was published by New York Times in 2015. It's showing cosmic selves. That means this is us, human being, and you see it is made from all star darts. All elements are there. So we are something, part of the space where we have made from all these space elements. But there was one question, even in 2015, 5 years ago. Why can't we see phosphorus? Everything we are finding, but we cannot see phosphorus. And we have been searching for life form for a long time. Right now, the question is it because of phosphorus we are not able to find any life form outside? Okay. And then we have started to look for phosphorus. We have found phosphorus in a number of places, but it is not abundant. In our solar system, it is abundant, but we haven't found abundant phosphorus any place. Then we found this is a supernova explosion from remnant from supernova explosion it formed. This is called Cassiopeia A, and we found phosphorus here. So that means we can say phosphorus is created when we have supernova explosion. But still, we don't see phosphorus produced in all supernova explosion. So it is an issue, and we have to study. If we find something, we should be ready to identify that is phosphorus, and we can analyze the environment. If we find, what these telescopes do, they collect the photons, the light, right? And they split, they take out the photons, and so they see the spectrum. And from the spectrum line, they can say, oh, that object has oxygen or iron, etc. So we have to know about phosphorus so that we can also do that kind of identification. Okay. Right. So this is the recent study. You can see, no, this is our department at Ohio State University is involved with this apogee project. Is under, there are all kinds of sky surveys. So this is a slow and digital sky survey. So in this project, they are trying to find what are the elements in space we can detect that are in our body. So you can see these are the large hydrogen, carbon, nitrogen. They found all signals in various places, and phosphorus is red. We have phosphorus, but we don't find much phosphorus, just tiny bit here. So you can see that for some reason, it is not abundant in the space yet. So this is just, I got this picture from Wikipedia, and phosphorus, we know we use it in industry, fertilizers, detergent, etc. And we know that it glows and light. It glows, it gives out light. But one thing about phosphorus is highly reactive. It's very reactive. Because the spectrum is not visible, so we did not study it. So it is the least studied element we have. So how do we study phosphorus? Now I'm coming down to our underlying science. How we can study things? It is through physics. And all the students, the physics, I'm just saying you are in a very good field. Okay, this is the field that Sam was saying. It is a good field. It gives a basic background to many areas of science. So this is a picture of atom and electrons going around. Being in physics, you know that they don't go like this, but it's just a picture because electrons have particular orbit. Okay, so they have quantized. We call quantized because they don't travel in between the orbits. So we know that, right? 1s, 2s, 2p, those orbitals, the electrons move around them. So what will happen if an electron decides to go to an upper level? So it has to have some kind of energy to go up. So it will be, then we call it an excited state of the atom. But all excited states have limited lifetimes. The electron has to come down. So the energy it got to go up there has to be given out so that it can come down to its own orbit. That comes out as a photon, okay, which we detect. When it absorbs the photon, see it is absorbing photon to go up, then we see also that part, in the spectrum is called absorption line. And if it comes out and gives out a photon, that photon comes out as an emission line. So, okay, this is the spectrum. I'm pretty sure you have seen in your books. See, these are the energies for electrons. There's nothing in between, right? Energy, ground state, excited state, because of the quantized or fixed orbit. So these are fixed levels that electrons can go, but there are infinite number of levels. That means it can go to infinite number of levels and give out infinite kinds of photons. So this is just showing the photon wavelengths. Okay, so it can go through a large, but a part of it only is visible. But because of this quantized state, we can do spectroscopy and we can get a lot more information. So this nature has provided us the tool to understand a lot of things, including black holes, or you can say merger of black holes. So what happens when the light goes through, for example, a prism? Then when it comes out, the photons of different energy will go to will make different angle. So that's why now red one is here, purple one, blue one, like that. So this is we call spectrum, right? Because you are separating out the colors or the energy photons this is for sunlight, right? For sunlight. But if we have, say, carbon, it is giving out some kind of light, and we let it go through a slit, and through when it comes out also, the law follows the diffraction. Photons will go to different angle depending on its energy. So we can separate out the energy of the photon. So this is like the spectrum of carbon. So for example, we see a line at this energy in the astronomical spectrum. Then we say that, okay, that astronomical object or that star has carbon, because carbon line is seen in the spectrum. So that's how we do spectroscopy. And spectroscopy is natural, it is happening. You see rainbow in Bangladesh, and also this is the rainbow at Niagara Falls in New York. You can see that very visible. Okay, now we'll talk about the photons. We are all interested in photons because in space we have objects, we study them by collecting the photons. So how these photons are created, there are 4 atomic processes. I'll mention each one. Those atomic processes either absorb a photon or give out a photon. So if we get the photon and we analyze, and we can find out a lot of information, but we have to give the underlying science how to analyze these photons. So one kind of photon is created when an electron goes from, say, energy level 1 to energy level 2, which I just mentioned, and then it drops out. So it can absorb the photon and give out a photon. So it will absorption line, emission line. Okay, this is we call photo excitation, also de-excitation. Okay, and we always calculate parameters. The parameters for this particular atomic process is called oscillatory strength, or also it is now connected to this quantity. It's called Einstein A coefficient, or we call it radiative decay rate. Okay, these we always calculate these kind of quantities for this kind of excitation or de-excitation. Okay, so this is the spectrum that we produced. So there are 3 other people who are also working with me. So this is the spectrum. So what we do, we study that kind of excitation and de-excitation. Okay, and from those A values of what we did, we created this spectrum of phosphorus. This is phosphorus 1, means neutral phosphorus. You knock out 1 electron, it becomes phosphorus ions. In astronomy, they call phosphorus 2. You knock out 2 electrons, you call it phosphorus 3. So these are the lines, coming from those excitation. So this kind of spectrum, we can predict and tell, the observers, when you find, for example, a line like this at this energy, so that spectrum, if you find this line in the spectrum, we can say, okay, phosphorus 2 exists in that astronomical object or star or in space. Okay, so this is the thing we can predict as a physicist. You can do it. All right, and whenever we study, we always like to check the accuracy of our results. See, there's a discrepancy I told you in the Venus observation. So what we do, whenever we get some results, we do the accuracy checkup. So we a value calculated, you cannot see because it is, the numbers are very small. So there is we always compare our values and some other accurate values, whether we agree with each other or disagree, because that gives a measure how good quantities we are producing. So this is just a table. So I just one process. All right. So and now I'm going to talk about the second atomic process, which involves a photon and an atom in the space. It is not only space, it is happening around you also, because we have light around you. So this is an atom, electrons are moving, and a photon is traveling, the photons. Then one of the photon is absorbed by an electron here. And then it becomes so much energetic that it not only it got excited, it doesn't need to be excited and come back. It has freed in itself and going to space. So we call it ionization. Now it has gone free. This atom has 1 less electron. So because photon was used for ionization, we call it photoionization. And this is a very common process in space. Whenever you want to study, because stars give out a lot of photons, right? We see them in the sky. So those photons, and in space and the stars, there are all kinds of elements. So they absorb those photons and ionize. So this is one most common process that we need to study. So because you're in physics, I will say a little bit about the process. So this is an ion, okay, just symbolic ion, and it absorbing the photon, and then 1 electron is ejected out, so it has become more charged, positive charge. So this is the photoionization. This is called initial state, that's the final state. And we call this just direct photoionization. and we can calculate the quantities. But it can also happen that, initial state and final state, there's one state forms in between. What happened? The photon is absorbed. The two electrons, instead of one electron, two electrons are excited. And that excited state is called autoionizing state. It has a name, and it is a very important state because it introduces a resonance in the process. What is resonance? Like you have some process, you have sudden rise in the probability of that event happening. So that means probability of ionization will go up significantly if this state forms. And this forms all the time in nature. So whenever we do theoretical work, we have to make sure that this state is included in the theory. Okay. Now, the quantity we usually calculate for photoionization is called cross-section. Okay, photoionization cross-section is called sigma pi. All right. Where it is happening all around you and space. So we are talking about how to detect, let's say, phosphorus lines. So we are looking for a spectrum from space. So this is a picture. It's called Lambda Centauri Nebula. So it is a gaseous nebula. You can see stars and you can see a lot of photons around. So all these elements, so photoionization is happening all the time in this place. So that means because photon is absorbed, that means we can see in the absorption part of the spectrum, photonization process. It is also happening a lot in our own sun. This is, you can see this in a corona, this outside atmosphere of our sun. And there are a lot of photons and excited electrons, everything, but it is happening all the time in our solar corona. All right. So how does it look like? Photoionization, how do we detect? So this is a feature of photoionization of phosphorus 2. It was measured by my colleague Guillermo et al. So he measured at this place. There's something called advanced light source at the Berkeley Lawrence National Lab. Okay, this is the lab. It's a part of University of California in Berkeley. So he measured. His team measured this spectrum. Then so comes my role because I do theory. So to determine whether all these lines are the real lines of phosphorus 2 or they are noise, and if it is like this, what kind of phosphorus they are. Ground state of phosphorus or excited state of phosphorus. Okay, so now this is what I did. This is the actual experiment they did. And bottom ones like my theory using some method called R matrix method, which is the best method to study atomic processes. Okay, so you can see in this feature, people think, oh, maybe most of the spectrum, they are part of the ground state. It is true. So you see this rise going like this feature, you can see here, going up and going down, in those. So these three lines for photoionization, they belong to three levels of the ground state. So we can see that the beam that Guillermo had largely made of the ground state. But then they saw this peak. So we can see that there's an excited state, and that excited state is giving this peak. So it at the same position. That means it has produced there. And also there's, even though they are weaker, but you can see signals, they also are coming from a particular state called quintet acid state. So these are, you can see here other lines, they match. So what you can question why they're so broadened and not here. So whenever you see a theory, that means these are ideal situation, and we should expect to see all of them. But in experiment, we don't see the whole thing, because experiment, the detector has some width. It is not exactly at that energy. So you have some broadened feature. You have some external field. All these things, density of the beam all together broaden the features somewhat. But we can see most of it. The more we see, the better it is. We say we benchmark each other. Benchmark means we experiment and theory agreed with each other. Okay, the third process, which again involves a photon, is called electron ion recombination. You know ionization, right? Ionization means the element or the atom will have less number of electrons. It could be one less electron or more. So what happens, one ion is like this, somehow it is ionized, so there was a vacancy. And electrons are always traveling around us in the space everywhere. Even though space is empty, it is not completely empty, absolute. There are also electrons are moving, atoms are moving, they interact, and slowly they come together through very weak gravity and slowly form stars. Okay, so anyway, so what happens, this electron finding a vacancy, it decides to join the atom or the ion. Okay, so it joins it, but when it joins an atomic system, we call bound electron. And when it was outside, it is free electron. It has more energy, and when it goes there, it should have less energy. What it is doing, it gives out a photon energy to join this atom, so it is less energy. These photon, they show up as recombination line in the astrophysical spectra. This recombination line you can analyze, okay? So that will be in the emission spectrum because photon is coming out instead of absorbing. Okay, so here electron is joining the one ion and then a photon comes out. So this is again direct, we call it radiative recombination. But if it happens just like a photoionization, in between it forms a doubly excited state like this, we call an autoionizing state forming. And whenever it forms, it introduces a resonance in the system. And resonance means, the probability of high of recombination at that particular energy. So I'll show you where this process is happening. This process is happening all over in space. This is another picture. Another nebula is called Crab Nebula. You can find a lot of beautiful pictures at NASA website. So this crab, you can see, the plenty of photons. And so photoionization is happening. That means electrons are moving, and plenty of electrons have plenty of ions for this process. So usually there's a balance. Photoionization is happening, then electron ion recombination is taking place. So plasma is in an equilibrium condition. Okay. But if in space, this is just space, is a bunch of galaxies here, but in space, in between the galaxies is empty space. As I mentioned, even though it is empty space, nothing is there. It is so empty that we cannot create that kind of vacuum on Earth. So even electrons are moving and atoms or ions are moving. Even in that, when they come toward each other, they combine in even the empty space, and recombination is happening, and the photon start to travel, and which we catch through the telescope, and we study the recombination process. So I just like to mention, so we, Nahar and Pradhan unified method, we developed this method long ago, and this is a very precise method to study this particular process because it was a complicated process. The radiative recombination, the other one is called dielectronic recombination, could not be studied together, even though they are happening together in nature. So we developed this theory to combine those together and study the process. So how do they look like? Okay, here is the spectrum that I produced for electron ion recombination for phosphorus 2. Okay, so this one and the lower one, they are basically the same spectrum. You can see that this is the photoelectron energy. So it shows where recombination is peaking. At this energy, you have more recombination probability. And I put some arrows. That means when the recombining ion have excited state, at that time usually there's a peak. Okay, so you can see a peak at all an excited state of the recombining ion, because this is from a publication, so you can see these arrows. So this spectrum is made from the this upper spectrum with multiplication. The reason I produce this, because this kind of spectrum is measurable in lab. So there are setups which can measure this in a spectrum. So what we usually do often, for modeling, so like I'm in between. There are people who do observation, there are another group who do modeling, and there are people in between who create the atomic data which will go to the model. So when I calculate that, these kind of features are needed for modeling. What you saw, what we do temperature average. Okay, so because in the star, temperature varies, from inside to outside. So we have to have temperature dependence of recombination so that we can model a particular place of the gas plasma in the star. Yeah, so there's, you don't have to know much except that it looks like recombination goes down at certain point, they peak. This is for various levels, not only ground level, various excited levels, how recombination process goes with various temperature. Okay, and this is the one, I'm giving it because you are in physics. uh, Total recombination rate coefficient going like this with temperature. That means at low temperature recombination dominates, and then it goes with high temperature. And this is a very important temperature, because typically this is the temperature region where the ion like phosphorus 2 will exist in the plasma. So this is so unified method, our method can determine the feature very precisely in this region. And then there's a high temperature, we have doubly excited state produced at high temperature, it peaks. And that when temperatures go very high, it just goes down smoothly. Okay, so this kind of feature is needed to know ionization fractions. That means how much phosphorus 2 is there in the plasma. It is very important. Those are like diagnostics. What is the density? What is the temperature? Those are diagnostics we need for modeling. We have to find out the information about the plasma, and that gives us also information how they are formed, what will compare, and then we can compare with other stars. Then we can characterize various star system. Okay, the last one, which also involves photon, is called, we call it electron impact excitation. So an electron is colliding with an ion. So it gives out part of the energy. So this ion is excited here. Okay. And then what will happen, as I mentioned, it cannot remain excited for a long time. It has to come down. So this electron is going out, this projectile, but this one will come down giving out a photon. And this photon we catch to study the environment. And this is also a process happening all the time. It's most common process, and it is a very important process to study astronomical or astrophysical spectrum. So this is just a drawing. Electrons are traveling and finds this electron. One electron collides, excited, and it is going out in other direction because it has given out part of the energy, and this will come down and photon will come out. The quantity that we calculate is called collision strength. Why it is very important, I'll show you. Okay, so this is just a picture of something we call ULIRG, ultra luminous infrared galaxy. Okay, this galaxy is kind of not very old, and lot of stars are forming inside, so it has a lot of dust inside. Okay, and you are creating a lot of photons, and all the dust and elements, the photons you are creating, they all are absorbed by other elements, so they cannot escape. If they don't escape, we cannot study the object. But what happens to electron impact excitation photons? Those photons often have very low energy. Okay, so they just do a little bit excitation and the photon comes out. Those photons are not very popular. They are not absorbed by dust, because they don't match. Most of the time they don't match their excitation energy. So those photons can escape this kind of system and come out, and which we can collect and study, okay, the object. So that's why this process is very important to study. So what is the physics? How does the physics look like for this process? This is what we see. It's a electron energy, because excitation, and this is the collision strength, the one quantity we calculate. Again, we see lines. These are again resonances. So resonances, they are happening all the time in all atomic processes. Okay, I mean not the excitation when they are bound. So photoionization, electron ion recombination, and also an electron impact excitation. So that means, like for example here, the possibility of excitation is very high. That means there'll be photon emitted, at this energy. All right, so we calculated that. So this is for phosphorus 3. So this is the energy diagram for phosphorus 3. We are focusing only to this, low excitation. So low excitation photons are the ones which are not popular, which don't match excitation of other uh, elements. So they are the one which can escape. So we studied that, and this is the, with temperature, so we can effective, the collision strength. So what it is showing, there's a huge, you can see bump at a particular temperature, right, in this range, and that is the temperature of planetary nebula plasma. Planetary nebula means, the almost the dying, death state of a star. A star, they are born and they die. So planetary nebula is, dying star. It is dying. Okay. So because all its hydrogens are gone right now. So this will help us to see the, or get the diagnostics of the plasma. Okay. So I have discussed all 4 atomic processes. Now, I'd just like to say that I belong to 2 international projects. One is called the Opacity Project, other one is called the Iron Project. The purpose of this project is to study atomic processes in detail with as much accuracy as possible and calculate all quantities parameters, using supercomputers. For example, I use the facility at the Ohio Supercomputer Center. So we can calculate all the parameters, so that when we predict something, so we can predict it accurately. Like, Venus, there's a large discrepancy of phosphine prediction and the observation. We want to narrow that discrepancy gap. Okay, so that's the purpose, objectives of these 2 processes. And it started long ago in 1983. Papers started to come in 1987. Okay, so it started, because of this kind of large discrepancy of this kind of Cepheid variables. It's called, this particular one is called RS puppies. So that's how this project started, is continuing at this time. And because it has been continuing for such a long time, involving a lot of people, and you can see that, people from all over many countries. So we study and underline science of this astrophysical spectroscopy. We have solved many problems, still solving. We are finding new physics. In like photoionization, we develop new theory. Like for electron ion recombination, we call it unified method. And and we produce large sets of atomic data which can go for modeling. And all those data have formed 4 atomic databases. One is called TopBase in France, which is at France. TipBase, which is also at CDS in France. OP servers, it is at Ohio Supercomputer Center. And NORAD atomic data, which is in the astronomy department of the Ohio State University. Okay, so Pretam mentioned this book. This book, has, it starts with undergraduate and goes up to the graduate level. So it is a bridge between astronomy and atomic physics. But the last slide I want to show, to encourage you to become member of American Physical Society. Okay, you can go to my website and download the form and apply. All of you should apply and become part of an American Physical Society. It is the largest, network of physics community, and it has many benefits. And you can be free members. All right. I'm very pleased to meet all of you and for the opportunity to talk to you about some physics. All right. Thank you.
Thank you, madam, for your wonderful session. So I think students have learned a lot of things in astrophysics and atomic astrophysics. So if you allow, we can start our discussion session. So we have got some question in inbox and in comment also. So why phosphorus is important in
Okay.
astrophysics?
Phosphorus
The first
because
question.
it is a basic element of life. So we know that we cannot form without phosphorus. So if you want to find a living form outside, we have to detect phosphorus. It will give us the clue that there is some living form out there. So that's why it is very important to study phosphorus.
So there's another question: is the energy of photon always
Yes.
come with a discrete
See,
value?
see, electrons, they move around in a particular orbit, so they are quantized. So they can go to one orbit to another orbit, but not in between. So it is always fixed energy. It absorbs fixed energy, gives out fixed energy. So they are always constant. Yes.
Thank you, madam. So I have got another question in inbox. So maybe I need to check the message. So once. So how R matrix method is used to calculate the
Okay.
various
Our matrix
observable?
method is a method how you tackle the quantum space. So you need to solve the Schrodinger equation, right? So even I think third. So first,
Yeah.
Newton's motion we know when we see actual classical motion, but when you go to quantum level, it is equivalent to Newton motion. We use Schrodinger equation, right? But Schrodinger equation, when we have an atomic system and we describe that atomic system with a wave function, then the wave function has it goes up to infinity ideally. But if we want to do integration, study all this and electron interaction and go up to space, we cannot solve it. So what R matrix does, it divides the space, into two parts: inner space and outer space. So inner space, we just deal with all the complexity of the atomic system, and outer space we simplify. Okay, it is more like hydrogenic system. Okay, so we combine them and then we can solve the problem. So it helps. Once we get the wave function, then good wave function, and our matrix can do that. The other part is that I mentioned about in between state, auto-ionizing state, which introduces resonances. Only our matrix can solve it. So when you write a wave function, we introduce those excitation in the wave function, and our matrix knows how to solve it. It can solve that matrix. It forms, instead of it's a single equation, it becomes a matrix. So it knows how to solve it. That's why it is the most powerful method to study atomic processes.
Thank you, madam. So as you don't have any questions, so we should conclude our discussion session, sir, madam. So so please say something about our next generation physicists who are in a bachelor level or master's level. So so you have succeeded in your life. So you started your life from Bangladesh, and now you're one of the best physicists in the world. So could you tell me about something for our students? So if anybody want to be a physicist, so what the basic things he or she
Okay.
first need
Basically,
to
is
do?
that you have to believe that physics, you are already in physics, and physics can provide a lot of things. And physics is something, it is not simple. Not that many people can study physics because it needs concentration, it needs perseverance, and what should I say? You also, it needs detachment. When you study physics, you cannot just say, "No, I'm going out there and play." You can do that, but you need lot of concentration. But this is a difference. So physics is subject where need all these things. It doesn't mean your brain is not capable. Your brain is capable. Only thing is that you have to think that, okay, I have to detach. I have to concentrate on solving my problem. And when you do something, you remember, right? Something worth, which is special. If you want to achieve something, it will not be easy, right? If it is easy, then we'll get achievements, everyone, nothing is special about it. So you have to to be perseverant, toward your study. So your brain is there. We have so much brain, we don't use the brain. Just use the brain, and I think you'll do wonderful. And remember that, make effort. So sometimes, you cannot solve it in time. Oh, my homework is due and I'm not able to finish it. Well, you make effort. If you make effort, our book says, that's what I read in Islam, you get 1 credit. But if you're successful, you get 2 credits. But if you don't, try, you will never get it. But if you try, the chance is high that you will get it. And maybe it takes time for some people. Sometimes, depending on the problem, sometimes it takes less time. It doesn't matter. But main thing is that you try your best. That is, I would say, one thing. And one thing is that now research is very important. Whatever you are studying in the books, they form your foundation. But if you want to contribute to the advances, you have to do research. Without research, you cannot make advances. Your university will not be known outside, and no matter how good you do, outside will people say, what is this? Okay, Pabna University of Science and Technology. So if you publish things, then it become more known outside. People say, oh, the student, he or she is from that place. So I would say that, please study, love your physics. It has application, medical application, industrial application, everything. You just have to concentrate. That is all. And also detach. You have to detach yourself. What I say to my female group, that keep 2 hours every day, at least 2 hours. See, 24 hours, you can take out 2 hours, right? You sleep, do other things, you spend time, social activities. Keep 2 hours for yourself to study. And when you take that 2 hours, you forget about everything. You just think about your own brain and your own study. Okay, make a promise or practice that I will spend at least 2 hours without in those 2 hours means this is only with detachment. I am just doing nurturing my own brain. And
Thanks, madam. Yeah, for your nice advice.
Yes, other thing I like to say that um, don't be afraid to ask question. Sometimes it seems like foolish. Okay, you become fool for a minute. That's it. But after that, you know what's happening, right? You are not supposed to know everything. You just know. Even if someone gives a talk which is not my area, I have difficulty. I have to really follow it to understand what that person is saying. So don't think you are expected to be expert in everything. You are expected. Max Born. If you heard, I think Neil Bohr. Neil Bohr. Pitam Neil Bohr.
Yeah.
He admitted he could never follow seminars.
Oh.
Because seminars to him, because they think the science is so much outside his own thing. he admitted that he could not follow what the other science is doing. So don't feel bad. You just do
madam.
best. That is all you can do. Okay.
Actually, maybe it's our main barrier. So we are not used to asking question. So we have to break that barrier first, maybe.
Yes.
So, madam, you are always our inspiration from my student life, and I have a dream to talk with you. Now I am doing my program with you, and I feel proud, madam, to doing this program. And I started this webinar to encourage our students in this corona pandemic situation. You know that all the world are suffering with this problem, so we cannot continue our normal program inside the campus. So all the students have to they have to go back their home, so they are not in a good situation. They may not have a good time to study. So actually in that time, actually I thought, okay, should I do something to encourage and for those students so who are studying physics, but they may not love in physics, but I think we should do something for them also. So what's our physics means, and for those physicists who come from this country and now in the good position in the world. So I am actually trying my best to encourage them. And thanks all of you, and like you people. So you are always inspiration, and I'm feeling proud today that you accepting our invitation, and we have completed our webinar with you. So thanks, madam. And I hope by this webinar, many of our students and many of we actually inspired lots to feel love in physics, and actually we can do good in physics by your advice. So thanks again, madam. And our department actually want to say thanks so for accepting our invitation, and thanks for your last slide to invite for being a member of APS. So I have already done my application, and I have already told my colleagues also for doing that. So thanks again, madam. So hopefully in the near future we will arrange another webinar, and after the COVID-19, when everything is okay, I'll invite you in my university for face-to-face program, and then we'll be very proud, and our student will be very happy in the if it will happen in our campus. So thanks again, madam.
Okay.
So bye for today. Good night.
Thank you, and pray all the best for everyone, and Assalamu alaikum.
Alaikum salam, madam. Assalamu alaikum, madam.
Walaikum salam.